Okay, we start now. Gravitational field topic. First question is stpm 2017-2018. Question 7. Okay, which graph shows the variation of gravitational force F between 2 point masses with separation R? So all the graph is F against R. Okay, so what is the relationship between F against R? So it's from the Newton's law. Okay, Newton's gravitational law state that F is directly proportional to the product of the masses. Okay, M, capital letter and small letter to distinguish between them, divided by R squared. Okay, R squared is separation between the two the two masses. Okay, so this means that G is constant value, M also constant value. So therefore, F is inversely F is inversely proportional to R squared. Okay, this one is wrong lah. Okay, inversely proportional to R squared. So inversely, which one? This is decreasing. The two A and B is decreasing curve. So be careful. So the value of one F inversely proportional to R squared is not at here lah. Here 0 supposed to not to be touching the y-intercept. So therefore it must be the answer must be A. Okay. So here to here is means on the surface of the earth. Okay, it has a value here for R. Okay. So inversely proportional is must not pass the y-intercept. Okay, so be careful with this question. Student make mistake here because of the y-intercept here. Okay, next we go to question 2. The gravitational field strength on the surface of the moon is 1.6 meter per second. So if the moon is assumed to be a sphere with a radius of 1.7 times 10 to the power of 6 meter, so what is the mass of the moon? Okay, so you are given the G value, gravitational field strength, and then the radius of the sphere 1.7 times 10 to the power of 6, and we are going to determine the mass of the moon. So from the G, M, and R here, so the equation is gravitational field strength is Gm per R squared. Okay, so we substitute the values given. 1.6 is G. G, capital letter G, gravitational force constant is 6.67 times 10 to the power negative 11. So mass of the moon, and then radius of the sphere 1.7 times 10 to the power of 6. Don't forget the square. So the answer for M is 6.9 times 10 to the power of 22. Okay, so D. So no problem for this question. Just memorize this formula for the gravitational field strength. Okay, number 3. Which graph represents the variation of gravitational potential V with distance R from the center of the Earth for region R bigger than radius of the Earth? Okay, R is Earth. Okay, radius of the Earth. So V against R. Okay, gravitational potential against R. V is for gravitational potential, and U is gravitational potential energy. So you must know how to distinguish between the V and U. Okay, so the formula for V is negative Gm per R. Okay, negative Gm per R. So the R here, no square. Okay, no square. So it means that V is inversely proportional to R. So inversely and then negative. So that's mean on the negative side. Okay. So A and C out. So B, negative side, and it's a curve, hyperbolic curve. Okay. So the answer is B. Okay. So any problem in this question? No, So we go to question 4. 2 points A and B, okay, which are at different altitudes from planet Z, are shown in the diagram below. The work done by the gravitational field to bring a spacecraft of mass 5,000 kg from A to B is 5 times 10 to the power of 10 joule. So what is the gravitational potential at A if the gravitational potential at B is negative 5 times 10 to the power of 7 joule per kilogram? So you are given the mass spacecraft 5,000 kilogram, okay, and then the work done is 5 times 10 to the power of 10 joule, and then you are given, we are going to determine the gravitational potential at A, so represent by the VA, and given gravitational potential at B, okay, this is VB, negative 5 times 10 to the power of 7 joule per kilogram. So we are going to determine the relationship between work and V. So what is the relationship between work and V? Okay, so work is change in gravitational potential energy. Okay, this is from the work energy theorem in chapter 4. So work is change in gravitational potential energy. So change in gravitational potential energy is final minus initial for U. So the spacecraft is brought from A to B. So that means B will be final. So UB is the final. UB minus UA. So for the change in, must always start with the final. So UB minus UA. And then U equation is GMM per R. And don't forget the negative. So at B is GMM per RB. So this M, small letter and capital letter, is mass for the spacecraft, and for the planet, capital letter for the planet Z. So UA also the same negative, GMM per RA. So RA represent the distance of the spacecraft from planet Z at position A, okay? This one is position B, this one at position A. So we get to relate with V. Now we are going to relate with V. So V is GM per R. So that means GM per RB is VB times the small letter M here. Okay, so it become negative VBM. And at position A, so will be VAM. Okay, so we substitute V equals to GM per R into both of the equation of UB and UA. So we get this. Okay, understand or not? Okay, so don't forget here minus, minus, plus. Here minus. So that's mean it's negative VM plus VA, not enough space. So I put, we go to this part, this side. Okay, refer to this side. Okay, now we can substitute the values given. So the work done from A to B is 5 times 10 to the power of 10 joule. Okay, so the mass we can factor out because here is the same. Then factor out, so we substitute 5,000 into the equation, and then we also substitute VB. Don't forget, don't make mistake with the negative sign. Okay, here negative already, but the VB given in the question is negative 5 times 10 to the power of 7. So you substitute here together with the negative sign, then plus VA. So we get negative, negative become plus. Now we bring to the right, divide it first, okay, by 5,000, then minus this one. So we get negative 4 times 10 to the power of 7, 10 to the power 7 joule per kilogram. So the answer is C. So if you make mistake with all the sign here, you won't get the answer. So for the U, remember that for the U and V, in any calculation, must put together the negative sign. Okay. For F, depends. If you use a vector diagram, no need to substitute the negative. Okay, calculation for F. But calculation for U and V must always bring together the sign with the equation. So understand or not? Any question on this number 4? Okay. So message from message. No, I think okay. So we go to back to the PowerPoint. Question 4 just now. Okay, we continue with question 5. Okay, question 5. A satellite of mass m goes around the Earth of mass m in an orbit of radius r. If the satellite moves to a new orbit of radius r per 2, which is true about the total energy of the satellite? Okay, so this is the Earth. Okay, so this is the satellite moving in the orbit with radius r. Now the satellite is moved to the second orbit at radius r per 2. So radius means measured from the center of the Earth. In this case, is the planet is the Earth. Okay, so to determine the total energy, okay, so from the ABCD only, so all mention about decrease, increase. So that means this is related to the change in total energy. The question asks for total energy. Okay, so what is the change in total energy? Change in total energy will be E final minus E initial. So total of energy at initial position here, and then at final position here. So must be very careful which one is final, which one is initial. Okay, so we use the symbol for change in total energy, delta E. So what is the equation for total energy? So we have kinetic energy, potential energy, and total energy. So you must memorize all the equation for the energy. So 3 types of energy: kinetic energy, potential energy, and total energy. So for total energy, the equation is negative GMM per 2R. Okay, 2R. So for final will be RF lah, final. GMM is constant value. And don't forget again, okay, is a negative. For kinetic energy, it's the same, GMM per 2R, but no negative. So be careful with E and K. So for E, total energy got sign negative in the equation. Okay, so we do the same for EI, but this time use RI. Okay, now the change in energy will be, we substitute the value of R. So for final will be R per 2 because the satellite is brought to here. So substitute R per 2. Then the RI here is R. So this is initial position R. So now simplify, cancel the 2 or bring the 2 up. So negative 2 plus 1 will be 1 lah. So the answer is negative GMM capital letter per 2R. So this is the answer. So A and B are out already. So which one? C and D. So to determine which one C and D, you refer to the negative sign. That's why it's very important to substitute together with the negative for the equation of total energy. So finally, you will get negative. So negative means decrease, okay? So the answer is C. So must very be careful with the sign. If no sign here, you will get the answer wrong. You will get the answer. Okay, so any question with number 5? Okay, so silent mean
Teacher, can you
yeah.
explain the third part again?
The third part, which one? This one or this one?
Above that, yeah. There.
Third step, you substitute the RF. So RF will be R per 2 because the satellite is brought from this position to this position. So this is final. So RF is R per 2 lah. And then the RI is initial, right? So you substitute because R and R2 is given. Okay, you must substitute with the given value into the equation. This part is the equation only, general equation. Okay, so this part is the substitution part. Then you solve, you solve. So this one use the form 1, form 2, form 3 maths lah. This one cancel, you get this. And then for to minus these two, okay, to perform the subtraction here must equate the denominator, right? So this is 2r, so here also must times 2. So above times 2, so means negative 2 plus 1. Negative 2 plus 1 is negative 1. So the denominator just now we equate as 2r, because the times 2 just now. Okay? Be careful. You must expert this calculation method is from form 1, form 2, form 3. Okay,
Okay.
not? Can I?
Cher,
Okay.
I was wondering when they say about total energy, does that mean we are referring to the gravitational potential energy?
Yes. Potential energy plus kinetic energy. E is total energy is the total of potential energy and kinetic energy. So we have proved this equation in one of our lesson. So you can refer to the PowerPoint note how to derive this total energy equation. Okay. So this is what we get lah. GMM per 2R. So this is fixed already, the equation for total energy. Understand?
Okay, thanks.
Okay. Any more question? Okay, if no, we go to number 6. Okay, question number 6. The period of a satellite in a circular orbit depends on, so the for F equals to ma. Okay, so gravitational force from Newton's law, from Newton's gravitational law, F equals to gmm per r squared, and the I repeat, circular orbit. Okay, look at the word here, circular orbit. So that's mean the satellite move in a circular motion. So we use the concept of circular motion where the resultant force, okay, the centripetal force are not resultant. The resultant force is a centripetal force. So the centripetal force is provided by the gravitational force only. So therefore, is equals to the gmm per r squared. So the centripetal force is given by mr omega squared. Okay, on the right side, the centripetal force is provided by the gravitational force. And on the right side, we substitute r omega squared into the equation because this is this is a circular motion. Okay, so this is where this equation comes from. Okay, from F equals to ma. Okay, so to determine the period, we use mr omega squared. Okay, to determine the speed, you use mv squared per r. Or for circular motion, another equation is mv omega. So which one to choose depends on the question. So in this case, we are going to determine the period. So you substitute mr omega squared. Okay, now omega here, angular velocity is equals to 2 pi f. And also f is 1 per t. So therefore, angular velocity also 2 pi per t. Okay, because square here, so both must be square. Okay, now we can simplify here, cancel the m, so we get t squared per r cube, because r here cross multiply, we get r cube. On the right side will be here squared 4 pi squared, gm bring to the right side, cross multiply, we get per gm. Okay, now see what the period depends on. Okay, so this one actually Kepler's third law. Okay, so the answer is C, because here the distance of the satellite and the t value, they depends on each other. So period depends on r. The rest for constant, pi constant, G also constant, 6.67 times 10 to the power of negative 11, and the mass of the Earth, Earth in this case is Earth, planet Earth. So m also constant. So therefore T and R change. Okay, so the answer is C. Okay, any problems with this equation? With this question? So if no, we go to question 7. Okay, question 7. A stone is thrown vertically upward under gravitational attraction. Okay, which graph represents the variation of potential energy U, kinetic energy, and total energy of the stone with its height h? Okay, assume that air resistance is negligible. Okay, so a stone is thrown vertically upward. Okay, so the graph, all the answer given here, A, B, C, D, is energy against the height, h. Okay, the height. And then the question also draw three in one energy. Okay, U, kinetic energy, and total energy. U is potential energy. Okay, so for the stone thrown upward, okay, we use principle of conservation of energy, because we have all the energy involved here: potential energy, kinetic energy, and total energy. So we use principle of conservation of energy. So principle conservation of energy state that total energy is constant. Okay, so that means the initial total of initial energy equals to total of final energy. So we use EK because the question here use EK to represent kinetic energy. Our textbook use K only for kinetic energy. So we follow the question EK to represent kinetic energy. So U, gravitational potential energy, same as in the book. E, total energy, also same as in the book. Okay, so at initial position, the total of energy is kinetic energy plus potential energy. So final also the same. Final kinetic energy plus final potential energy. Okay, then we substitute the value of kinetic energy. So for initial to project or to throw upward the stone, it needs a velocity u. Okay, so this velocity u is constant. Okay, because to throw upward one time only here means one time only. So the u is constant. Okay, a stone is thrown vertically upward. So u is constant. So you substitute u as a initial velocity half mu squared. So plus u from the surface of the earth. H means the height from the surface of the earth. Okay, h. So from the surface of the earth as a reference also is a 0. Okay. So for final, it can be anywhere on the surface of the earth, above the surface of the earth. So the velocity changes. The velocity changes. So can be V1, V2, V3. So generally we write as V. So V change as it move at different height. Okay. And then plus the mgh. Okay, so M constant, G constant, H is also different. Okay, so the V and H change depends on each other. The rest all terms, the rest all constant. So now we bring half mv squared to the left side. Okay, then the other we bring to the right side. So we get this equation, half mv squared equals to half mu squared minus mgh. Okay, so we can simplify this equation. No need also can. Okay, we just bring this to the right side because it's easier for you to see the relationship with the graph later. So this means kinetic energy at the position, any position at any position, because it depends on the V. So at any position, V is changes. Okay, so now mgh, so m constant, g constant, I just write k, so that this value don't disturb you later when we are going to relate with the graph later. So we just put sk as a constant, and then this one also constant, right? So the stone is thrown upward with this velocity, initial velocity u. So this is considered as c. Okay, why are you C? Because we are going to relate with the linear graph. Okay, maths or at maths also you've learned y equals to mx plus c is a linear graph. So C and D is out already. The answer C and D. So it's a linear graph. So the equation form here is in the form of linear. Okay, linear equation. Okay, linear graph. So where y is the ek, so y-axis is the ek here. Okay, and then the c is the y-intercept. So it has y-intercept value. Okay, both a and b has intercept value. This is for ek. And x h. Okay, x is h. So look, refer to the all graph. The x-axis is h. Okay, x-axis is h, and k will be the gradient. So the gradient will give you mg value. Okay, gradient, but we don't bother about the mg. Okay, because not asked by the question. Okay, the question just asks the shape of the graph. So which one, A or B? So refer to the ek. This is ek line. The ek line, the answer is B. Because it's a straight line and it has y-intercept value C. Whereas the A question, look at the ek line. The ek line y-intercept value is 0. It starts at the origin. So therefore, A is not the answer. Okay, the answer is B. Okay, so we do for ek enough already because A, C, D don't have the correct ek. Okay, for the E total, always constant, right? So correct lah here. And the total must always between ek and u, ek plus u. So it must on the line here. Cannot be here. This is the line for E total for A question. This is the line for E total. Okay, for the C question, correct also. So the best is B. Okay, and the U, as ek is decreasing, so U is increasing. So they are opposite of each other. Okay, the best answer, the correct answer is B. Okay, any question for 7? Question 7? Okay, hope my explanation is clear. Okay, next we go to number 8. Okay, silent means understood lah. So we go to 8. Two satellites orbit the Earth with the same period. Which quantity for both satellites must be of equal values? Okay, equal values. So that's mean same as just now. So I repeat so that you can memorize easily. Same thing as just now, we use centripetal force provided by the gravitational force, GMM per r squared. Okay, and the centripetal force is equals to mr omega squared. So why omega? Because we are going to relate with period as asked in the question, period. Omega is 2 pi per t. Okay, then we rearrange the equation, we get t squared per r cube equals to 4 pi squared per gm. This is all constant. So for the same period, if t same, so r also must be the same. So the answer is C. From the same methods, but different. They just use a different question. So the answer is C. T and R must be the same. To have the same period, R also must same value. Okay, any question for question 8? Okay, clear. So we go to question 9. A satellite is said to be geosynchronous if it appears to remain over a fixed position on the Earth. Okay, on the Earth. So geosynchronous, which statement is not true about the geosynchronous satellite? So what is meant by geosynchronous satellite? So it means that, refer to the animation here. Okay, you observe from the Earth the satellite. It is as if not moving. It always on top of you. If the satellite is on top of you, so it will always be there. But actually, it is moving with the orbiting the Earth. Okay, it is moving, orbiting the Earth. So why this happens? So you must know the characteristic of the geosynchronous satellite. So this one is the not true. Okay. So when for the satellite to become like this, okay, always you observe always on top of you, it must orbiting the Earth with the same period as the Earth. T, okay, period T must be the same. This is one of the characteristic of the satellite. So therefore, I don't repeat again the question. Okay, straight away we use this Kepler's third law. So T squared per R cube equals to 4 pi squared per GM. Okay, so the R cube is T squared cross multiply lah. So you got T squared GM per 4 pi squared. So all this is a constant. Okay, constant value must be at the okay, the T value must same as the Earth. So T also is a constant. Okay, where the period of the Earth is 24 hours. So you convert to second. You substitute the G value also, M and 4 pi squared. So you will get R also is a fixed value. Okay, so T and R is a fixed value. So geosynchronous satellite must be at a certain position and also at same period as the Earth, but better to be on the one more characteristic is it on the equator. Okay, on top of the equator, it is the best position. Okay. So if you calculate 24 hours, it is equals to the 8.6 times 10 to the power 4. Okay, so A is the true. The not true is the B lah. The satellite can be placed in any chosen orbit. So it cannot be at any chosen orbit. Okay, because T is constant. And when we substitute into this equation, we get R value is one value only. So it's a constant value. So the satellite cannot be placed anywhere you like. Okay, so cannot be placed at any chosen orbit. So the wrong answer is B. So this C is correct. It moves in the same direction as the rotation of the Earth about its axis. And D also correct. The satellite moves around the Earth in a circular orbit under the influence of the gravitational force. Okay, because this equation comes from the gravitational force. The centripetal force is provided by the gravitational force. Okay, so D is the correct answer also. Okay. So any question for this question 9? Okay, here if you convert 24 hours to seconds, so you get about this value. So 8.6 times 10 to the 4 second. And then the answer for R is about 36,000 kilometers. Okay. So you calculate on your own lah, is these two value. Okay, so if no questions, means that you understood this question 9. So we go to number 10. So a satellite is moved from orbit S to orbit T as shown in the diagram below. Okay, so this is orbit S, this is orbit T. Wow, quite famous question for past year's question, okay, about satellite. So orbit S to orbit T. So which one is initial, which one is final? Be careful. S is initial, T is final. Okay, what is true about the energy of the satellite when it is moves from orbit S to T? So the energy, look at here, A, B, C, D, it all state about potential energy. So we can refer to the potential energy. So that's mean the work done is change in gravitational potential energy. Okay, because the answer here A, B, C, D all related to potential energy. So we choose the work done equals to change in gravitational potential energy. So it is UF minus UI. Okay, so you substitute the values of U. U formula is negative GMM per R. Okay, put the sign together with the equation negative, and the R will be R final, and the R for initial will be R initial at S lah. Okay, now we substitute, simplify the equation. Minus become plus. That's why you must put the negative together. Here become plus. Okay, now which one has smaller radius? Okay, initial or final? Initial has smaller radius. So what does this mean? As orbit S, initial has final radius. So that's mean this value GMM per Ri will be larger than GMM per Rf. Okay, because here smaller value. Okay, so the larger the denominator will give you the whole term here become less. Understand? So therefore, we can get the answer for this equation always a positive value because larger minus smaller. Okay, so larger minus smaller will give you always a positive value. Example for minus 2, 2, 10 minus 8, 2, 10 minus 5, 5. Okay, so always give you a positive value, larger minus smaller value. So therefore, positive means increase. Okay, increase in potential energy. So B and D out already. So between A and C. Okay, between A and C. So which one? Work is done against gravity or work is done by the gravitational field? So the answer is work done against the gravity. Okay, because it is brought to position T, S to T. So the work is done against the gravity. Okay, so this is the answer for question 10. Okay, any problem with question 10? Okay, the physics concept is very important, then followed by maths concept. Clear, Okay, so my explanation means that clear lah, no question. Okay, silent means understood. Okay.